Hello, I welcome you to the next tutorial for microwave-based non-destructive testing. Today we will learn how to use lenses to increase the spatial resolution and to suppress parasitic signals. Here I will give you some examples for the need of high resolution, that means for focusing. You know, rotor blades of wind-powered turbines are manufactured as two half shells, which then are bonded together. The distribution of the adhesive between the outer laminate and the shear web then cannot be seen from outside and cannot be inspected visually. A different NDT method is necessary. Similar structures and problems may arise at the wings of small aircrafts. The typical structure to be tested is shown here. We have a laminate of two thin plates of glass fiber reinforced plastic with a thick layer of balsa wood in between. This is outside, and here in the inner side we see in green the adhesive layer to bond the laminate to the shear web, which is not shown in this model. The laminate can be 40 to 50 millimeter thick, and the task is to non-destructively test from outside the adhesive layer inside for air voids. Because all the material is insulating, microwave testing is a good choice. Special challenges, however, are the need to detect rather small air voids and to suppress parasitic signals which are generated in this natural and therefore inhomogeneous balsa layer on the path of the microwave rays forth and back. These inhomogeneities are annual rings and adhesive layers between balsa parts, as we can see in this photo on the right hand side. Both mentioned challenges can be met using a microwave lens. We know lenses to direct optical waves, which are electromagnetic waves with very high frequency and short wavelengths below 1 micrometer. Microwaves are also electromagnetic waves, but with longer wavelengths between 1 meter and 1 millimeter. Therefore, appropriate lenses can also be used to direct microwaves. But because of the larger wavelength, normally larger sizes are necessary. Let's look at this planar convex lens in its use as a burning glass. Parallel rays are incident, then by the lens focused into this focal spot, and then they diverge again. This is in the homogeneous space. If, however, there is a particle with some different permittivity in the focal spot, Then scattering occurs in all directions, and a part of this propagates as reflections back through the lens. These reflections can be received by the antenna in which the incident rays were generated. The reflections only occur as long as the particle is in this small focal spot. That means when moving the test system up and down, then we have a very high resolution of the part to be detected. The lens can be designed according to the well-known rules of optical lenses. The important parameters of the lens are its shape and the refractive index or permittivity, which is the square of the refractive index. The lens can easily be fabricated by 3D printing, for example from PLA material. Here we see an example. Now we have to ensure parallel rays at the input of the lens. That could be done with a small radiator, like an open waveguide, rather far away. But that would cause unnecessary losses. Best is to use a closed wave transformer. A so-called corrugated cylindrical horn can do this. It produces parallel rays which are distributed homogeneously over the aperture. Here on the left side we see the coaxial port for the connection to the transmit receiver. On the aperture, on the right side, the lens is added. Then we have the combination here. Here we see the model used to test the system. The sandwich consists of balsa, nearly 40 millimeter thick, with GRP plates on top and bottom. The 3D printed PLA plates simulates the adhesive layer, while the lowest GFRP plate simulates the shear web to be bonded. The PLA plate can be interchanged by various versions which contain different flat bottom holes which model the air voids. We can see these plates here below. The voids range from 30 millimeter times 30 millimeter times 3 millimeter down to 0. The lens-based detection system is moved meander-like on top of the model, and the lens is designed to focus such in the PLA plate. This video shows the test in the horizontal plane. The corrugated horn with the lens scans in meander type manner on the one side, and on the back side there is the sample mounted, the plates. The coaxial cable leads to a network analyzer which acts as a transmit receiver and an initial display is on the screen. Here we have an overview again. Here we see the test results from 30 times 30 times 3 down to 0. The amplitude of the reflected signal is shown in the upper lines, and the lower lines show yellow areas in which the amplitudes are above a threshold level, which is given by the noise. The noise is the residual noise from the inhomogeneous balsa wood, which could not be eliminated by the lens principle. However, most of the balsa noise was eliminated by using the lens. The detection limit in this case is a flat bottom hole of 10 millimeter diameter and 2.5 millimeter thickness in a depth of more than 40 millimeter, mostly through balsa wood. That is a rather good value. We have learned how in microwave testing lenses can be used to inspect with high resolution layers deep under the surface of devices and at the same time suppress noise signals. That's it for today. Thank you for watching. Goodbye.